Hi everyone, good day. So we are going to discuss about block diagram. As we already encountered the idea of block diagram, this was mentioned in the report of Monaris and Padika. So a block diagram is composed of a blocks, arrows, others, and it has an inputs and an output. So all going to discuss that further here. So let's get started. Firstly, we'll discuss some important points of block diagram. So we have 3 points here. First, block diagrams are pictorial representation of a control system. So we are going to see some pictorial representation of a control system and also block diagrams. Point number 2. Block diagrams representation is used to build a mathematical model of a control system which can be emulated in a computer. It is a good point to understand that nowadays systems are analyzed on a computer by the use of a software, and in that case the block diagram representation plays an important role because it can help to build a mathematical model of a control system. And lastly, the point number 3, block diagram representation is used to calculate the overall transfer function of the system. As we all know that to find out the output with respect to any given input, we need the transfer function of the system, and the block diagram representation helps to find out the overall transfer function of the system. So now we are done with the discussion of introductory points of block diagrams. We will now discuss the elements of block diagram. We'll start with the basic block diagram representation of a control system. As we can see that it consists of blocks and having 2 arrows. The arrows of the signal which goes into the blocks represents the input, and the block itself represents the transfer function of the system, and the signal which goes out of the block represents the output. But this is just a basic block diagram representation of a control system. Practically, the control systems are more complex in nature. They consist of multiple subsystems, interconnections of many blocks, which are connected with branches and arrows. So to analyze those complex representations of a block diagram, we need to discuss some more elements of block diagram, like the summing point and the takeoff point. So now we will move on to the discussion of summing point and takeoff point. So first is the summing point. A summing point or a summing junction in a block diagram representation is the dynamic summation of 2 or more signal. So whatever we want to add to 2 or more signals in a block diagram, we will use a summing point. So that is the symbol of the summing point, which is used to add 2 signals. It is highlighted in blue. So if this signal is x1 of s and this signal is x2 of s, then the result signal will be x1 of s plus x2 of s. On the other side, if this signal is x1 of s and if this signal is x2 of s, then the result signal will be x1 of s minus x2 of s. So the polarity plays a very important role here. If the polarity is positive, then the signal will be positive. And if the polarity is negative, then the signal will also be negative. In the first diagram, the polarity of the both signal is positive, and hence the signal are added, which is positive sign. In the side diagram, the polarity of one of the signal is negative, and hence it is added with a negative sign, since we are using the summing point or the summing junction in order to add 2 or more signals. In a block diagram, we can also call this point as another point. So now we're done with the discussion of summing point. I will now discuss the takeoff point. So the takeoff point is also called as takeoff point or a branch point. So the takeoff point in a block diagram representation is a point where the signal branches out and goes concurrently to the other blocks or a summing point. Or we can say that the takeoff point in a block diagram is a point where the signal distributes to several other branches. So let us understand this with the help of this diagram. So this is a takeoff point. The signal distributes, this is a branch of a block diagram, and we can see that from this point the signal distributes into this branch. Similarly, in the other side, this is the takeoff point, and this point distributes the signal into these three branches. If the signal is R of S, then we can distribute the signal with the help of this takeoff point among these three branches. So just like this. So this is the basic use of takeoff point in the block diagram. It distributes the signal from one branch into several other branch. In that way, we are done with the discussion of summing point and takeoff point. So we'll now move on to the reduction of multiple subsystem. As we already discussed, that the practical control system are complex in nature. They consist of multiple subsystems, and in order to find out the overall transfer function, we need to reduce those multiple subsystems into a single block. So we'll discuss this under the topic of reduction of multiple subsystems. So we have 2 points here. So to start with the first point, in order to calculate the output with respect to any given input, we need the overall transfer function of the system. So we all know that the transfer function is an important parameter in order to find out with respect to any given input. And moving on to the next point, when the system is complex, that is having multiple subsystems, then we need to reduce the complex block diagram representation into a single block, and so that we will able to determine the overall transfer function of the system. So now we have the idea that the primary target is to find out the overall transfer function of the system. Let us take an example of practical control system. So this is a practical control system. It consists of a multiple subsystem. It also consists of interconnections of different blocks connected with different branches and arrows. And if you want to calculate the overall transfer function of this multiple subsystem, we need to convert this overall system into a single block representation. So a single block, where this block represents the overall transfer function. And the procedure by which we can reduce this complex block diagram representation into a single block diagram is called a block diagram algebra. And the block diagram algebra is based on a certain reduction rules, which are called the block diagram reduction rules. So we're going to discuss the block diagram reduction rules next. Block diagram reduction rules. So first, the rule 1 of a block diagram representation is the representation of a closed loop system. So we have a closed loop system here, in which the input is RS, the forward path is GS, the feedback path gain is HS, and the output is CS. We can see this as a negative feedback system. And if you want to convert the system into a single transfer function, we need to calculate the transfer function of the system, which is GS over 1 plus GS times HS. But for simplicity, we can write it as G over 1 plus GH. Similarly, in the case of positive feedback system, we can replace this block diagram representation into a single transfer function, which will be equal to G over 1 minus GH. So this is the rule of the number 1, which is representations of a closed loop system. We will now move on to rule number 2. So according to rule number 2 of block diagram reduction, when the blocks are connected in series or cascade, their gains are multiplied. So we can see here in this rule 2, block diagram representation, these are two blocks are connected in series, because the output of this block is the input of this block, the first block. So the first block, or which is G1, and the gain of the other block is G2. And if you want to convert this whole block diagram representation into a single transfer function, then we need to multiply these two gains, and we will have a single block of G1 and G2. We can also prove this rule. Let us assume that the output of the first block will be x. So the output is x and the input is rs. So we can write g1 is equals to x over r, and we could also write g2 is equals to c over x. Now if we multiply the gains of two blocks, the g1 and g2, it will be equal to x over r times c over x. Now if we can have c over r, which is the equal to the overall transfer function of this system. So moving on to rule number 3. When blocks are connected in parallel, their individual gains are added. In this block diagram representation, these two blocks are connected in parallel. As you can see, when blocks are connected between two same points, then we can say that the blocks are connected in parallel. We can see here this blocks having gain g1 is connected between the takeoff point and this other. Similarly, this block having a gain of g2 is also connected to the takeoff point and to that other. That is why we can say that these two blocks are connected in parallel, and hence if we want to convert this block diagram representation into a single block, we need to add these two gains, and the equivalent diagram, this block's diagram representation, will be like this. So the transfer function will be g1 plus g2. So let us check the proof of this rule. We can have the output is equal to r multiplied with g1 plus r2 multiplied with g2. So if we take r common in this equation, we can have c is equal to r multiplied with g1 plus g2. If we take r to the left hand side, we will have c over r equal to g1 plus g2, which is the overall transfer function of this block representation. And hence we can say that when the blocks are connected in parallel, their individual gains are added. So in that way, we are done with the rule number 3. We will now move on to rule number 4. The rule number 4 of a block diagram reduction is regarding the shifting of takeoff point before a block. Let's consider this block diagram representation as what you can see in the screen, having a gain g, and this is the takeoff point, which is after the block. So the output of this takeoff point will be equal to the c, which is equal to r multiplied with g, since the output of c will be equal to g multiplied with r, and that is rg. Now if we wish to move this takeoff point before this block, then in that case we need to do some changes in the block diagram representation. Let's consider the block diagram representation once more. First is the block of gain g, and let us assume that we have shifted this takeoff point without any changes before the block. Then what will be the output of this takeoff point? Yes, it will be equal to r, because it is connected to the branch having input r. But in this case, the output of the takeoff point was r multiplied with g, and the output of the takeoff point must be constant when we shift this takeoff point before the block. So in order to maintain the output of this takeoff point, we need to multiply this takeoff point with a block of gain g, and in that case the output of this takeoff point will be r multiplied with g. So we can say that in this block diagram representation, if we want to shift the takeoff point before the block, we need to multiply the takeoff point with the gain of this block. Now moving on to rule number 5 of block diagram reduction, which is regarding the shifting of takeoff point after the block. Consider this block diagram representation as it was shown in the screen, in which the block is having a gain of g, and this takeoff point is present before the block. Now if I ask you, what is the output of this takeoff point right here? So yes, it will be r. Now if we wish to move this takeoff point after this block, then how we can do it? Let us just check this out. Firstly, we'll consider the block itself, and then consider this takeoff point, which we are shifted after the block. Now what is the output of this takeoff point? So it will be c, which is equal to rg. So the output of this takeoff point is equal to rg. But before the output of this takeoff point is equal to r, so in order to maintain the output of this takeoff point, we need to make this equal to r, and for that sake we need to multiply this takeoff point which with a block of gain 1 over g, and then the output of this takeoff point will be equal to r as it was previously. So from this point, we can say that if you want to shift a takeoff point after the block, then in that case, we need to divide the takeoff point with the gain of this block. And what is the idea behind this? Yes, the output of this takeoff point must be the same before and after being shifted of the takeoff point. Like in this case, that the output before shifting of the point was R multiplied with G, and that's why the output after shifting must also be equal to R multiplied with G. And that is why we multiply the block of gain G. Similarly, in this case, that the output before shifting was R, and therefore the output after shifting must also be equal to R. And that is why we multiply the output of this takeoff point with the block of gain 1 over G. And that's all for rule number 5. So moving on to rule number 6 of block diagram reduction is regarding the shifting of takeoff point before and other. Consider this block diagram representation as what you can see in the screen. This is the block, this is the other, and this is the takeoff point. The input of the other are R1 and R2. That is why the output of this other will be R1 plus R2. And this block having a gain of G, and that is why the output will be C is equal to R1 plus R2 multiplied with G. This is the output of the system. But we are interested with the output of this takeoff point. The output of this takeoff point is R1 plus R2. Now, if you want to shift this takeoff point before this other, then how can we do it? Let's check this out. If you want to shift this takeoff point before this other without any change, let's see what happened with the output of this takeoff point. Consider this block diagram representation one more time. We have shifted this takeoff point before the other. Now, what is the output of this takeoff point? Yes, it is equal to R. In this case, when the takeoff point is after the other, the output of this takeoff point was R1 plus R2, because the output of this branch is R1 plus R2. But the output of this takeoff point must be the same before and after shifting, and that is why the output of this takeoff point must be R1 plus R2. So in order to make this output R1 plus R2, we need to add R2 in this takeoff point. So for that sake, we represent this block diagram one more time, in which we are having the takeoff point before the other. And now, what is the output of this other? Yes, of course, it is R1. Now, now in order to make this output R1 plus R2, so we need to add R2. But in order to add R2, we need one more other at this point. And now we are able to add R2. And hence that the output will be R1 and R2. So now we can see that the output of the takeoff point is R1 plus R2. In that case, we can say that if you want to shift a takeoff point before the other, we need to add one more other. And in order to maintain the output of this takeoff point, so in order to maintain the output of this takeoff point, so now we're done with the rule of number 6. So we'll now move on to rule number 7. The rule number 7 of block diagram reduction is regarding the shifting of takeoff point after the other. So let's just discuss this diagram representation as what you can see in the screen. So in which we have a blocks and other and a takeoff point. So for that sake, so the other is having the two input R1 and R2, and hence the output of this other will be R1 plus R2. And the block is having the gain G, and that is why the final output will be C is equal to R1 plus R2 now in order to make multiplied with G. In this case, we are having our takeoff point, which is present before the other. And now what is the output of this takeoff point? Yes, it is equal to R1. Now, if you want to shift this takeoff point after this other, then how we can do this? Let's try to shift this takeoff point without any change. Let's discuss the block diagram one more time, in which the rest of the thing are the same, but we are now shifting this takeoff point after the other. Now, what is the output of this other? Yes, this now are R1 plus R2. We can see that the output of this takeoff point before the shifting are R1, but now when we have shifted this takeoff point after this other, the output is equal to R1 plus R2. But we all know that the output of the takeoff point must be constant before and after shifting, so we need this output equal to R1. For that sake, we need to subtract R2 for this output, and for that sake, we need one more other. So let's discuss this block diagram representation one more time, which we are having the takeoff point after the other. And the output of this takeoff point is of course R1 plus R2. And now our target is to make this equal to R1. For that sake, we need one other at this point. And now we are added the signal R2, which is negative polarity, so that we can subtract signal R2 from this takeoff point. And now we can see that the output of this takeoff point is equal to R1. So now we can see that the now we can see that the shifting of takeoff point before after other introduce one more other in a block diagram, but we need to maintain the output of the takeoff point. So we will now move on to the rule number 8 of block diagram reduction, which is regarding the rearrangement of others. So consider the block diagram representation in which two others are connected side by side, as what you can see in the screen. One input to this other is R1. The second input is R2. Hence, the output of this other will be R1 plus R2, which is the first input of this other. Second input of this other is R3. In that case, the output of the second other will be R1 plus R2 plus R3. And now if the block is having the gain of G, then the final output will be C is equal to R1 plus R2 plus R3 multiplied with G. Now if you want to rearrange this other, that is, if you want to shift this other to the left side and this other to the right side, then how can we do this? Let us check this out. So consider this block diagram representation in which we shifted the other to the left side of the right side. Now the input of this other is R1, and the second input to this other is R3. So now the output of this other will be R1 plus R2. Now the second input of this other is R2, and as we can see that the output of the second other will now be R1 plus R2 plus R3. And again, the block is having a gain of G, and the final output will be equal to C is equal to R1 plus R2 plus R3 multiplied with G. So we can see here this output is the same as before the arrangement, and that is why we can see that we can rearrange two sides by side other without any change in the block diagram representation. So this was a simple rule, and now we're done with this rule. Now moving on to rule number 9 of a block diagram reduction is based on the shifting of other before and block. So consider this block diagram representation. We are having a block, having an other, so we can see that the currently this other is present after the block. Now if the input of this block is R1 and this block is having a gain, then this output will be R1G, which is the output of this other, and the second input of this other is R2, and then the output of this other will be C R1G plus R2. Now if you want to shift this other before this block, then we need to make some changes, and what are those changes? Consider this block diagram representation one more time, in which we have shifted this other before the block. Now the input of this other is R1, and the second input is R2. So the input of this other will be R1 plus R2, and this is having the gain, then the final output will be C. Now moving on, C is R1G plus R2G, but we can see that the output of this other R1G plus R2. But when we shift the other for the block, we are having a block. We will now move on to rule number 10. Rule number 10 of a block diagram reduction is regarding the shifting of the other after the block. So consider the block diagram representation as shown on the screen, having an other and having a block. We can see that this other is currently present before this block. Now, if the input of this other is R1 and the other input is R2, then the output of this other will be R1 plus R2. And if this block is having a gain of G, then the output will be C is equal to R1 plus R2 multiplied with G. Now, if you want to shift this other to the right of this block, then we need to make some changes in this block diagram. Consider this block diagram representation one more time, in which we are shifted this other to the right of this block. We can see that the initially this was present before the block, and now we are shifted this other after the block. Now, if the concern of the input is R1, then the output of this block will be R1G, and this second of this other is R2 as it posed in this case. So the output will be equal to C is equal to R1G plus R2. For this case, that the output was C is equal to R1 plus R2, and multiply with G. If you open the bracket, we can see that the R1G plus R2G. So we can see that this factor of G, when we should multiply with R2 in order to maintain the output. So already we here having the input of this other as R1G. If you multiply a block of gain G with this at input, we will have R2G as an input. And finally, we'll have the output as R1G plus R2G. So let's check this. If you multiply a block of gain G with this input, then the output of the block will be equal to R2G, which is the input of this other, and now the final output will be equal to C is equal to R1G plus R2G. We can see that the factor G is now multiplied with R2. If we take a G common, we can have C is R1 plus R2 multiplied with G. And now we can see that the output is same in this way. You can see that if we want to shift this other after this block, then we need to multiply the gain of this block with this input. So we can say that if shift the other before the block, then we need to divide the gain of the block from the input, which is shifted. And if we shift the other after the block, then we need to multiply the gain of the block with the input, which is shifted. Like in this case, this input is being shifted as we're shifting the other to the right, to the right of this block, and that is why we need to multiply the back gain in this output. So in this way, we are done with the discussion of block diagram reduction rules. So to all of my, that's all for my report, and thank you for watching.